Okay, welcome to the next lecture. We This will be the series will be eighth lecture on cams. So let me boost up the mic audio a little bit. Let me get a sip of water here. So we left in the last lecture with this pitch curve, which we derived analytically, and we also did. Earlier with the graphical, I have plotted both together to show you that the match is quite good. So what we did graphically and analytically at the pitch curve level is quite reasonable. So what we want to do is now proceed forward. I want to derive the equation for the cam profile. So we will do that again. We will do that first for the radial follower and then for the offset follower. Although you may ask me, why do I want to do both of these? I could do this for the offset follower, and if I substitute E equal to 0, I should get the same equations. But nevertheless, we will go ahead and let's follow that. Okay. So so first thing that if you recall, what did we do? We drew a roller circle of radius r at certain points, and then the center of the roller, of course, is on the pitch curve, and so I'm going to draw that here. So I'm showing you here. Of course, this is from our graphical method, so that you can visualize. So this is part of the pitch curve. The purple one is the pitch curve. The trace point is out here. You can see H is the trace point. I've drawn a roller of the radius. In our case, we have taken that to be 5 millimeters. So we draw that circle, and what you notice, of course, this is the radial line. This is the axis of translation for a radial follower, and this brown line is basically the normal that is drawn to the pitch curve. Now one of the advantages that you have in GeoGebra when I constructed this is that when I have a particular curve, I can say perpendicular to that at that particular point, and it will draw the normal automatically. So that's the beauty of this. So I could actually physically measure this phi, and I can take the angle, and then from a graphical construction tabulate what the pressure angle. So this, by definition, recall that the pressure, this is called the pressure angle. This is the angle between the line of translation, which is in this case the blue line. This is the line of translation, and the normal to the pitch curve. So what does it dictate? Why are we worried about this? The pressure angle basically simply means, remember that the contact force, so here is the contact, right? So the contact happens at that point K. So my force is actually along this brown line. The contact force is along the brown line. I can now break that into two components. One which is along the translation axis, which is going to be the cosine component, and then there is an angle which is basically perpendicular to this component. Sorry, not an angle. The component which is going to be perpendicular to this, which is the sine component. So let's say the contact force is F. I have a F cos phi which is along the line of translation, and so now you can see that since I have a contact force, I have to have a way of maintaining. We talked about form closure, force closure. So I need to apply a force there is a force at the contact which tries to separate this out, and then I need to apply a force to keep that contact together. But I also have a side force. Remember that this follower is going to slide on a bush, and so therefore there is a side thrust on the bush, and we want to keep, so since it is F sine phi, I want phi to be as small as possible, because sine theta in 0 to pi by 2, essentially as the phi increases, the sine phi component increases. So the side thrust increases on the follower, which is not a good thing because it can jam the follower in the bushing. So so we would like to know what is the maximum what do you call pressure angle. See, we looked at what we call as transmission angle in the angle between the in the kinematic synthesis, between angle between the what do you call coupler and the output link, and we said that that should remain as large as possible, as near 90 degrees as possible. Here we would like this to be as small as possible, which is almost 0 degrees, right? When it goes to 90 degrees, then everything is basically going to be, of course it's not possible, but the large angles essentially mean that the side thrust increases. So, so essentially the H is basically the trace point, and K is the actual point on the cam curve where it is contacting, the roller is contacting that. So you can see that there is an angle which is defined as the pressure angle. Now we want to find the coordinates of K. That is essentially what we are trying to do. We know the coordinates of H. Remember, we have derived this in the last lecture video. I showed you the equation for H both for the radial, and the radial case is very simple. For the offset case, there's some additional terms due to the offset. Okay, now let's go back. Now the cam profile contact point is this. So AJ1 is basically the translation axis passing through H in the inversion. Those things we already know. Alright, let's go down. Now let's look at, again, I have brought the same figure out here, and then let's look at this coordinates. Now I want to find the coordinate of K, K1, as GeoGebra has labeled this, right? Remember, I have an axis which is plonked at the XY at A, which is the fixed axis, X1, Y1, which is a rotating axis, which is moving with, rotating with the follower in the inversion, which is rotating clockwise. So if I look at the coordinate in the X1, Y1 coordinate system, H has already been established. It is only along the Y1 axis, which is RP plus Y of theta. The X coordinate is 0, so this was done already. So the coordinate of H is basically 0 RP plus Y of theta. Now if I look at HK, the distance is basically the radius of the distance is basically the radius of the roller, and it is making an angle of phi from the Y1 axis. So therefore I leave this to you to sit down and visualize this, that the coordinates, the x1 y1 coordinates in the rotated axis are r sub small r, which is the roller radius, sine phi, minus rr cosine phi. So if I add the two, so if you look at what I'm really interested is AK, the vector AK1, so that will be AH plus HK1. So when you add the two, I get RR sine phi is the x coordinate of K1, RP plus Y of theta minus RR cosine phi is going to be my Y coordinate, Y1 coordinate. So sorry, this is in the actual fixed coordinate, sorry, AK1. So this is the x coordinate, RR sine phi, RP plus Y of theta minus RR cos phi. So so essentially we now have this is in the local coordinate. My mistake. We still have this in the local x1 y1 coordinate system. Now we can transform this and we get the coordinates in the xy fixed coordinate system. So if you do this, I have RR sine phi multiplying cos theta. Remember, the first row is cos theta sine theta. So I have RR sine phi cos theta plus RP plus Y minus RR cosine phi sine theta. The next term is minus RR phi sine theta, sine phi sine theta. And then I have RP plus Y of theta, which is a local Y1 coordinate multiplied by cos theta. So if we know what is phi for each theta, then essentially now we have the equations for the cam profile. So the equations for the cam profile is now derived, but at this point we know that the pressure angle comes into the expression, but we don't know what is this angle phi, right? So let's before we come and examine this relation, this is the rise part of the curve that I showed. Now what happens at the return part of it? So here is a point taken on the pitch curve and cam, these of course from the graphical construction like before, where it is on the return part of the curve. So what you see here is that the only thing that has happened is that the normal in the rise part was on one side of, so if you go back and look at that slide, if you look at this is, so I would say that it has rotated, if I look at the translation axis from there, I have rotated now along this direction. So now come back here in the return part. So here is my this thing. Now instead of rotating from here in this direction, I have now rotated and gone the other way around. If you want to imagine, both are like this, so I have rotated in the opposite sense. So therefore what happens is that the final local coordinates, you can see a small the RR, earlier it was plus RR sine phi minus RR cosine phi for the rise part of it. Here it becomes a minus RR sine phi minus RR cosine phi for the return part of it. So one could simply say that phi is replaced by minus phi if you want to think about it in that fashion. And therefore the xy coordinate system for the return part will have an expression like this. So in order to have a one single expression, what we do is we simply say that in the return phi is basically minus phi. So that is the way to visualize this. Now how do I obtain this phi of theta? Phi, which is the pressure angle for varying theta. Remember we talked about in the very first few lectures about an equivalent 4 bar linkage, and I remarked at that point it is very, what is the use of this, because at each and every position of the cam I have to come up with a new 4 bar mechanism with different link lengths, although that varying link lengths made it flexible, but to do a kinematic analysis is painful because for each configuration I have a different set of lengths that I have to deal with. But that concept becomes useful in order to do our derivation for this angle phi, right? So remember, the equivalent linkage at a particular instant or configuration has the same velocity and acceleration as the original cam follower mechanism, right? So what is the equivalent linkage? Remember that the follower is a slider. So here is the visualization of this. So remember how we constructed the equivalent 4 bar. We looked at the radius of curvature of the pitch curve. So you can see that H1H basically is, if you want to think of that as the radius of curvature of the pitch curve, of course of the cam is going to be H1K1. So that is going to be that. And of course the radius of curvature of the roller, which is the other body in this. So the cam is represented by this HK, H1K, and the roller is represented by HK. H1K is the radius of curvature of the cam at that instant, and HK is the roller radius at this instant pointed in this direction. So you have this mechanism. So and this of course H is of course the center of the slider, and it slides back and forth. All right. Now so if you look at it from the standpoint of if you look at this from the standpoint of the mechanism, this is a slider crank mechanism that we have. Essentially we have revolute joints. This of course is I12, the body 1 is the fixed body, 2 is the cam, and 3 is basically going to be the what do you call link 3 is kind of normal to the pitch curve, and 4 is of course the follower itself. So so 3 is which is normal to the pitch curve, and it makes an angle of phi to the translation axis, which is known. So this angle phi is, this is the translation axis, right, in the inversion. And this is the normal to the pitch curve at that particular point. All right. So now let us look at the instantaneous centers. I12, I23 is of course this particular point, I34 is of course the H, and then I14 is at infinity. So if I draw that line out here, the intersection of I34, I23 and I12, I14 gives me I24. So this is the location of point I24 for this equivalent linkage at this instant. Now what does that mean? Of course remember I14 is along the horizontal because the translation is vertical. So the I14 is at perpendicular to that at infinity. So we are drawing that through I12 here, and we have located I24. Now velocity of the I24 is going to be omega of the cam, which is omega 2, multiplied by I12, I24, if you visualize this to be a point on 2. Remember, it is also a point on the follower because it is common to both 2 and 4. 2 is the cam, 4 is the follower, which means the follower velocity, which is dy by dt, is equal to dy by d theta into d theta by dt. right? So if you split that in that fashion, you simply have dy by d theta, I'm going to call as y prime, multiplied by omega. So let me repeat those steps just for the sake of so here is a snapshot, the equivalent linkage. The equivalent linkage is constructed by locating the center of curvature. So remember my old potatoes that I had drawn a few videos ago. How did we construct the equivalent linkage? We looked at each of those bodies which are in contact. We said that the common normal is basically the link 3 coupler, right? The common normal becomes the coupler, and the common normal center of curvatures will form the end of those linkages, right? So this is the h is the center of curvature of the roller, and this h1 is the center of curvature of the cam pitch curve at that particular time. So therefore we join this, and of course the last one, the follower itself is a slider back and forth, right? So we get a slider crank mechanism which looks like this, which is the connecting rod at this instant. And from this we basically now look at the so having constructed this slider crank mechanism, which is the equivalent linkage, we now locate the I12, of course, is the center of cam rotation. Then I23 is this at this instant of time, which is the joint. This is kind of an artificial joint we are visualizing between the cam and this so-called coupler, which is the common normal to the cam and the follower. And then of course the follower itself is a slider, so that will be body 4. So 3 is something that is kind of artificially introduced. So 2 3 is this junction, 3 4 is of course the joint between the slider and this coupler, and of course 1 4 is going to be at infinity perpendicular to the direction of sliding. So we located I24 by Kennedy's theorem, so the instantaneous centers, and I located I24. Now I want to find out, we use the fact that I24 is a point which is common to both link 2 as well as link 4 and has the same velocity, right? So what is VI24 as a point on link 2? It is omega of the cam multiplied by I12 into I24, which is that distance. And remember, I24 is a point on the follower. All points basically have a velocity which is dy by dt, so which is omega times dy by d theta. So if I equate the two, it turns out I12 I24 is now simply y prime, which is the derivative. So if the upshot of all of this is that I12 I24 is now equal to dy by d theta. So obviously this helps us in locating I24. So I24 keeps sliding back and forth like this. So when y prime theta is maximum, of course it can go on this side, which means it is negative. On this side it is positive. So if I now look at this triangle A, I24, and go back to H, this angle is phi. So if you simply look at this as a right triangle, so if I look at A, H, I24 as a right triangle with an angle phi, tan phi is going to be the opposite side, which is I12 I24, which is y prime of theta, by the adjacent side. What is the adjacent side? The adjacent side, which is going to be rp plus y of theta. Okay, so the opposite side by adjacent side, which is this side, which is rp plus y of theta. So that is the location of the location of the point H along this, right? So therefore phi is simply tan inverse of y prime theta by rp plus y of theta. Now we have an expression, solid expression for phi in terms of not directly in terms of theta, but in terms of y of theta and y prime of theta. So implicitly it is dependent on theta. But the point to note here is, once I have fixed the follower motion, y prime theta and y of theta are fixed. So at any given theta, they take certain values. I can now, remember I wanted to make this phi as small as possible. So one of the ways to do this is to increase rp. Now this can be done two ways. I can have a base circle radius which is fixed and then increase the roller radius, but we don't do that normally. So instead, the other way to look at that is, having fixed a particular roller radius, now I can increase the base circle radius. Remember we said the base circle forms the size of the cam. So essentially by increasing the size of the cam, we can now get the pressure angle to be reduced. So now we have a formal expression for this, and we can do a similar equation for the return and show the same thing. So I will skip these slides. The only thing is phi is negative as y prime is negative. So therefore you will get a similar expression. Only thing, keep in mind that y prime of theta is going to be negative valued. So therefore phi becomes negative in that in the return portion of the profile. But the argument is essentially the same. So for the return, again we have an equivalent slider crank which has been identified. But as I remarked earlier, in one case, in the rise case, we had it to the right side of I12. Now we have to the left side of I12. So therefore y prime, essentially what that means is y prime is negative. We follow the same procedure, opposite side. This again is y prime of theta, and the adjacent side is rp plus y of theta. So we get the same equation. As I remarked, y prime is negative for the return, and therefore phi will be negative. Alright, so now the beauty of this is I can plot this. You can see that there is a location. So here is the maximum where y prime theta. So what happens, where is phi a maximum? So you can go back and look at tan phi is y prime theta by rp plus y of theta. So you can equate that to take a derivative with respect to 0 and then show where the maximum is going to be. In our case, it's roughly about, from what I can see, is about 45 degrees. Positive 45 degrees, negative 45 degrees, which simply means that the orientation has changed. So this is symmetric right now for the radial follower. So one of the ways I can, if I desire that it should be only about 30 degrees, 45 instead of 45 degrees, I can now increase the base circle radius and achieve a lower pressure angle. So here is from the CAM equation. Remember, the CAM equation was already derived for you. I just now, all that I did was, so here is where the CAM equation was. So the phi was something that needed to be found out. We did that, and we simply plugged that into this equation to generate the CAM profile, pitch curve and CAM profile. So earlier I showed you the pitch curve. Now we have the CAM profile, which you can see for 5 millimeters is what I have taken in this particular case. So we now have a CAM profile which is meant for anti-clockwise rotation, and the pressure angle is about plus or minus 42. A normal thumb rule, as I said, is to have it around plus or minus 30. So if we choose RP to be 65, the maximum pressure angle reduces to plus or minus 33 degrees. Now what happens if we introduce an offset? So that's the next thing that we are going to look at. In this case, so you can see that I went from 40 to 65 and basically reduced only the pressure angle by about 10 degrees. So you can see that it has some impact, but certainly the size of the cam becomes quite large. Now I just have an animation that I am going to show you. So let's I can't play this animation in my ocular. Okay, I think in your regular PDF you should be able to play this animation. It simply shows this going up and down. I'm sorry that in my Linux system it doesn't, the animation doesn't work, but it will work on your PDF if you do it through an Acrobat. So that's something that you'll be able to do. Alright, so I think let me kind of stop here. This is but what we are going to do is again repeat this exercise for the offset follower. We'll do that as another lecture, and then there will be one more thing that will be left after this, which is going to be a flat face follower. So let me stop the lecture out here, and then we will continue with the offset in the next lecture.